So it is my privilege today to moderate this session of the Dornsife Dialogues. And I'd like to start by welcoming our audience. Attendance in this dialogue series continues to grow thanks to your curiosity and interest in the insight and research of our leading USC Dornsife scholars and alumni. Today, I am particularly excited to be joined by two colleagues from the Department of Physics and Astronomy at USC, people who think about some of the biggest, hardest, and most fundamental questions in the universe, Professor Nick Warner and Dean Amber Miller. So I'll start with a quick introduction. Professor Warner is Professor of Physics and Astronomy and Mathematics at USC Dornsife. He is a theoretical physicist with expertise in string theory. He's going to tell us all about that. And he's currently working on understanding the quantum structure of black holes and black hole singularities. Professor Warner has been at USC since 1990. Before USC, Nick was on the faculty at MIT. And before that, he was at the University of Cambridge, where he did groundbreaking work with Stephen Hawking, one of the most brilliant theoretical minds in history. Today, Nick is joining us from Paris, France, where he's now serving as the project director of a large European Research Council-funded project titled The Quantum Structure of Black Holes and the Recovery of Information. Nick, it's a pleasure to have you here with us today.
Thank you. It's a privilege to be here. Thank you to the audience for coming along and listening.
Thanks. All right, and our second guest hardly needs an introduction. So Amber Miller is the 22nd Dean of the USC Dornsife College of Letters, Arts, and Sciences. She holds the Anna H. Bing Dean's Chair and a faculty appointment in the Department of Physics and Astronomy. Before that, she was the Dean of Science at Columbia University and led an experimental cosmology research group studying relic signatures from the Big Bang, with the goal of understanding the origin and evolution of the universe. Amber's research on measuring the cosmic microwave background radiation has taken her to do measurements at some of the most exotic locations on Earth, including Antarctica and Chile's Atacama Desert. And we definitely want to hear about that later as well. Since joining USC, Amber also started multiple initiatives at the interface of academic research, policy, and public engagement, including this very series, the Dornsife Dialogues. So Amber, thank you for joining, and I look forward to this conversation with you as well.
Thank you for letting me be on the other side of the introduction for a change. This is great fun.
Usually, that's right. Usually you're doing the introduction. Okay, so we're gonna get right into it. We're gonna be talking about some of the most extreme phenomena in the universe, literally out of this world stuff. And I thought a good place to start would be for each of you to take a few minutes and just get us all on the same page. So help us visualize what we should think about when we talk about black holes or the Big Bang. And Amber, I'm hoping we'll start with you. Help set the scene for us. So when it comes to understanding the birth and development of the current state of the universe, when we think of what cosmological research looks like, what kind of questions does one ask and try to answer, and with what tools? Please let us in. Yeah.
So cosmology is really the study of the universe as a whole. Where did the universe come from? How did it evolve? How did we all come to be? So it's kind of the most fundamental question in some ways that humanity has been asking since the beginning of time. But from a very physics-oriented standpoint, what is it that we're trying to understand? We're trying to understand where the universe came from and how did it evolve. And we have an amazing tool to study the universe because light travels at a finite speed. So why is that interesting? So a few things we know about the history of the universe. We know that the universe started very, very hot and very, very dense, and very likely microscopically small. And we can talk about that later. But as the universe started very small and dense and then expanded and cooled, it's not that the universe expanded into something so much as space-time itself expanded. And as it did that, we live in one place. There are other places in the universe that all were created or at least we think they were, our universe as we know it was created, not in a place, but at a time. So we think of the Big Bang as something that happened at a particular time everywhere in the universe. Okay, so how do we study that? How do we look back in time to see that event? Well, it turns out that you can think about the light travel time in terms of really simple things. Like if I look at the sun, I see it as it was 8 minutes ago. It has taken light that long to get from the sun to us. That means if the sun were to all of a sudden go dark or explode, we wouldn't know anything about that for 8 minutes. And as you go further and further away, you look at distant galaxies, you look at stars, you look at clusters of galaxies, you are literally looking back in time because it's taken light thousands or 100,000s of years or millions or even billions of years to get to us. And so if we want to understand what did the early universe look like, all we have to do is find those light particles that have been traveling to us all the way since that beginning of time. And fortunately, most of space is actually pretty empty, which means miraculously, you can actually do that. And it turns out that you can look using light, it turns out microwave light, but light, all the way back to when the universe was 380,000 years old. The universe is now about 14 billion years old. So that means we're looking at a baby universe. And you can actually make maps and literal photographs of the universe when it was 380,000 years old, which is before the formation of anything that we think of as stuff we know about in the universe, before stars, before planets, before galaxies, before anything that we can see and feel and touch. So that's kind of amazing. And we have a little animation just to give you a sense of what it would look like if you were to follow a light particle the other direction. So in other words, if you were to zoom away from the Earth, out further and further and further into the universe, maybe pause just for a second, because it's a little overwhelming. I'm going to tell you what you're going to see, and then I'll tell you what we're seeing. So you imagine this is traveling away from our Earth, and it goes very, very fast because it's very big. But first you'll see stars, then you'll see galaxies. This is real data collected from something called the Sloan Digital Sky Survey. And as you get further and further away, you'll see structures start to emerge on the very largest scales. And then you'll see not much of anything. And then you'll see something that looks like a big ball. And that's called the cosmic microwave background. That is that light that was emitted when the universe was only 380,000 years old. Okay, so let's go ahead and look at this, and I'll show you a little bit as what you're seeing. So this is zooming away from Earth. These are real galaxies that were observed by this instrument. Now you start to see the shape. You can see this kind of model-like shape where clusters of galaxies on the very largest scales, you can see areas that are denser and less dense. And then you can see things that look like sheets. Those are just where this survey observed. So this is not that there's big regions in that gap, that triangle, that don't have anything. It's just the survey only looked out in certain areas. So you're just getting slices of that observable universe. Now we'll zoom out even further and you'll start to see not very much. And then there is that microwave background. And what you're seeing there, it's going to look like a big ball. And what you're seeing is the observable universe. So in other words, if I look out as far back until we see when the universe was that age, I can look in any direction in the universe and I can see that light coming from all over that shows what the universe looked like at that age. And that, again, that's real data. That is a baby picture of the universe that you're seeing at the largest scales. And we can talk a little bit about the little modeled structure that you're seeing there. That reflects fluctuations in something like a plasma, kind of like the material in the sun. You're seeing little regions that are hotter and little regions that are colder. And you might, if you're sharp, notice that the characteristic of those fluctuations looks kind of like the characteristic of the fluctuations in those clusters of galaxies that were observed as we zoomed out. And we can talk about why we think that is the case later on.
Thank you, Amber, for that great visual introduction. Looking at the big kind of zoomed out picture there, literally, one can't just help but how insignificant we are on that scale of that map, and yet how amazing it is that we can actually produce and interpret, we'll talk about this later, this kind of knowledge. but I'm sure we'll talk about that a little bit more. So Nick, let's come to you also for a visual introduction. A black hole, of course, is one type of structure that is abundant in the universe. So walk us through the image we should have in our mind when we're talking about black holes.
Okay, so however you slice it or however you want to describe it, the thing that defines a black hole is something whose gravity is strong enough to trap light. And so there have been various conceptions of this over 200 years, but we currently use primarily Einstein's theory of gravity, general relativity theory. And in that framework, a black hole comes with two essential features, one of which is called the event horizon and the other is called the singularity. Now, the event horizon is, we think of as the surface of a black hole, but it's actually just a frontier. It's the boundary between what you can see from the outside and what you cannot see that is inside. And in fact, the event horizon is defined by the surface from inside of which light or nothing else can escape. So it's the surface of no return. Literally all events on the other side of the event horizon are invisible and undetectable and cannot influence an external observer. So once you cross the event horizon, you are utterly out of contact with the rest of the universe. But all that stuff that crosses the event horizon collects essentially or collapses into some kind of center or some object in the black hole called the singularity. And this is where gravitational compression in general relativity theory is thought to become infinite. And what happens is it must rip all of matter, whatever fell into the black hole gets ripped into its most fundamental constituents. And so there are two structures, they're different in different structures. One is the surface of the black hole. It is not a surface like a surface of a planet or a star. It's actually a perfect vacuum. It just defines the frontier between that which can talk to us and that which cannot from outside. Now, if you want, I want to get one subject out of the way. If black holes are actually totally black in general relativity theory. So the question is, how do you see them? And so for that, there's a very simple, nice sort of pictures, but basically you see them by their effects on their neighbors. So if you have a small black hole, we're talking something maybe 4 miles across, maybe a few miles across. But if it's next to another star, it quite literally starts stealing the other guy's lunch. But in the process of doing that, it strips gas off the star, and then the gas spirals into the black hole, and some of it gets incredibly highly compressed, and then some of it gets redirected and squirted along the rotational axis of the black hole. And so what you look for if you're looking for a black hole, a small black hole, one of the things you look for is the gas streaming across on the right of the picture, this disk and this spiraling disk called the accretion disk, and then the jets that come out of both ends of it. And so small black holes we see by looking for their effects on their partner stars. Now, large black holes in the middle of galaxies can actually eat entire stars quite comfortably. In fact, do this on currently the Milky Way isn't doing it on a great rate, but it still happens. So if you can start the animation, you should imagine this is a huge black hole. And by itself, I've highlighted it with a white circle, but by itself, you barely see it. You see it distorting the star field in the background. But when a star gets a little bit too close, it gets tidally disrupted and matter streams across into the black hole. And there you see this accretion disk again, but this is on a vastly larger scale, and the jet. And then that jet and the accretion disk are particular things you can see over vast distances. You can see them across the entire sort of, neighboring galaxies and all over the place. In particular, if you can cut to the next slide, we have plenty of animations where you can see these sort of nice animations and simulations and visualizations. But when you actually go out and look at the real universe and look for these things, if you can show the next slides, you see the smoking guns of black holes in the middles of galaxies. So this is M87 on the right. I think that's one of the NGCs on the left. But basically these jets and these accretion disks are the smoking guns of black holes in the cores of galaxies. And as we'll probably discuss a little bit later, we have even more direct ways now of seeing black holes. When the two neighbors are both black holes and they merge, they produce incredibly powerful gravitational waves. And we've seen them in the last few years in the LIGO, that stands for the Laser Interferometer Gravitational Observatory. But I think we'll get onto that later.
Thank you, Nick. So this was very helpful for both of you, starting with this visual introduction. So I was hoping now we're going to start digging in a little bit deeper and asking some basic questions about how we know what we know and what ideas can help us understand these phenomena. So of course, we use physics to try to get a fundamental understanding of everything around us, everything we can observe, right? So for many in our audience, maybe Newton's laws of motion may be an example they're familiar with. So they describe very accurately the behavior of everyday objects in our everyday experience. If I push or apply some force on something, doesn't matter what that object is, a cat, a rock, or even a fluid, even water, I can use Newton's laws and predict very successfully what the outcome of that will be. But we're now talking about cosmic phenomena that are way outside of our everyday intuition. So these are not the objects around us that we apply forces on. So what is the right physics? What does one even observe? How does one even observe? Nick, maybe we'll start with you since you've already brought general relativity into the view.
Okay, Newton is the thing you must remember about Newton is the theory is fantastic and is still fantastically accurate. It works really well in the solar system. In fact, I believe NASA and the flying Voyager out past Jupiter, I think the prediction was right within 1.5 seconds for when it would emerge from behind Jupiter over many years of flight. So Newtonian, and that was based on Newtonian gravity. So first thing is Newton was an incredible genius and his theory is incredibly good, but it's not quite good enough. And one of the shortcomings of Newton's theory is that it's action at a distance, but it's instantaneous action at a distance. And what that means is if I take something, a mass here, wiggle it, I take a planet and jiggle it up and down, we believe now, of course, the effect should propagate out or move out at the speed of light. But in Newton's theory, it's instantaneous. It crosses the universe and all places in the universe all at once. Moreover, in Newtonian gravity, light is uninfluenced by gravity. So a light ray is not bent by a gravitational field. But we now know experimentally that light is deflected by the sun. It's deflected and bent by galaxies and galactic clusters. So Newton's gravity does not play nicely with light. I think Amber's probably a lot more this way.
One thing I like to point out is, people say science gets overthrown. So we find out that the science we had before was wrong. And sometimes in some fields that's true, but in physics, it really doesn't work that way. In physics, once we have a law, Newtonian physics was found to work in human scales. So, the things we can see and feel and touch, building houses, building cars, building things that we interact with. But we didn't know what would happen when you started doing experiments with light, for example. And then when you start probing those edges, probing the areas that you don't know, then you start to see the things that let you know that you need more. And so when you say it's not quite right, it's a great description for that set of things that we're comfortable with. But way out in the cosmos, when you have things like black holes, things like the early universe, you start to realize you need something broader. And that, if you could just show that visual of Earth embedded in space-time. I like to show this. It's a nice way of seeing in the Newtonian world, you would say, okay, if you have an object like a planet, and then there's another object, the action at a distance means they're attracted to each other, but you don't know why. You just have an equation. In general relativity, you get the same equation, but what you see is that there's this new conceptual framework that tells you that there is a space-time metric, right? This thing that you see there, this diagram, that's bent by a big, heavy object. And the bending of that metric is why light is impacted also by gravity, because light travels along those lines. And when it sees a big, heavy object, it bends those lines and light is bent around that object in a way that Newtonian gravity just doesn't explain. And that opens up a whole other framework that helps us understand things like the way that black holes work, things like the way that the universe works. And I'll tease one other bit here, which is we know that Newtonian physics works on human scales. We know we need general relativity on the very largest scales, but on the teeny tiniest scales, like the scales smaller than an atom, Also, Newtonian physics isn't a complete description. And that's where you need another thing that was developed called quantum mechanics. And quantum mechanics describes the world of the very, very tiny. And one thing that kind of pulls black holes and the early universe together is that those are two environments in which quantum mechanics and general relativity are both needed, and they don't play so well together. So it tells you you need something even bigger that describes what happens in the very tiny and what happens in the very big and what happens in between. And that's the future that we'll talk about later.
So is it fair? Yeah, sorry, go ahead, Nick.
Sorry.
Yeah.
I was going to say that that's the thing that ties Amber's work closely to my work, is that the basic infrastructure upon which we work is general relativity theory. We're both trying to use gravity and Einstein's theory of gravity to describe the things we're looking at. So Amber's looking at the evolution of the universe, and that's how the geometry of the universe evolves. And what I do is I look at the things where the curving of the universe is so extreme that it traps light. But I'm lucky because I have a much easier job than Amber, because black holes, if you make them, they tend to sit there for a very long time. And so they don't change much over time. It's sort of like trying to understand evaporation of a puddle or something like that. Whereas Amber's trying to do gravity that's evolving so rapidly in time that it's incredibly difficult. But it's like trying to study, rather than the puddle, a stick of dynamite detonating. It's a much more dynamical and difficult calculation. But the beauty of the black hole is it just sits there for all time, well, not for all time, but for a very long time, not doing a whole hell of a lot.
So I want to get in a couple of minutes to this business of the intersection of quantum mechanics and general relativity, especially for black holes in the early conditions of the universe. But I also wanted to ask, now that we've introduced this idea of space-time, the very fabric of the universe and Einstein's general relativity, should I think of it as something like independent, just sitting out there in which matter is embedded? Or are we talking about these early conditions of the creation of the universe gave rise to this very thing that is space-time itself? What's the right way to think about this for our audience?
That's what we're trying to find out. Right. So we can roll the film all the way back to what we think of as the beginning of time. And we know the universe started really, really small. We think microscopically small, and we know then it expanded. But the ultimate question is, what created that little baby universe in the first place? In what is it embedded, right? I mean, is it embedded in some higher dimensional space? That would be really interesting. Could there be multiple universes? That's very possible. We really need to get at what created the universe in the first place. And so the work that our team is doing, although now that I'm a dean, I'm playing a small role, so I should give most of the credit to my collaborators. But the work that the cosmic microwave background field is involved in right now is trying to look past that microwave background sphere. So that sphere is light that was emitted at 380,000 years. And the idea is, can you look past that all the way back to 0 years? And there is actually an idea that the universe was created from a quantum type fluctuation. And the universe was very, very, very quantum mechanically small.
Because everything was so stuck together and close to each other, right? That's the idea.
Yes.
Yeah.
And that those fluctuations that you see on that ball were actually quantum fluctuations that were expanded to macroscopic scale. And then were the seeds of all of that structure that you see later in the galaxies and the clusters of galaxies. And certainly, we know that those quantum mechanics, so that those fluctuations that are seen in the microwave background were the seeds for structure. The question is, did they come from quantum fluctuations? And most people think very likely yes, because the statistics there are the same, which is very intriguing. And that gives us a clue about where the early universe, what was going on. And the interesting thing is that many theories suggest that in that expansion from microscopic size to small but macroscopic size, gravitational waves were generated. And those gravitational waves then travel from time 0 to when the microwave background is being emitted, and they shake the electrons that are emitting those photons and put little teeny tiny signatures in the microwave background that we can then go and see. And that would be a hint. If we see those gravitational imprints, that tells us that we understand something about the theory of that very first time t equals 0. So that's what the field's trying to do, is trying to see those teeny tiny little fluctuations on the fluctuations in the form of light that is polarized, actually. And that's the name of the game right now, is trying to get all the way back to time t equals 0, really to understand what is the fundamental nature. How would you bring quantum mechanics and general relativity together, which is, of course, then the same question that Nick is trying to answer when he looks at black holes, because that's another place where these two things have to work together.
In fact, there's a general relativity theory. We now believe, well, we know that general relativity theory doesn't play nicely with quantum mechanics. And one of the best laboratories actually for testing this sort of idea is an easier laboratory is, of course, the black hole. So Amber, this whole business of quantum fluctuations, we normally think of them as being incredibly small, things associated with individual atoms or perhaps molecules. And so Newton's theories fail to describe atoms, and we have to use quantum mechanics. But we usually think of it as just the very, very small. But also, in this, the theory of quantum mechanics tells us that what the vacuum, the thing that we think of as empty space, is actually a very complex dynamical structure in which there are fluctuations and oscillations, and particles come out of it, spontaneously appear in the vacuum and then disappear in this sort of constantly changing dynamical process. But we in the macro world cannot actually see that directly. But suppose you have one of these fluctuations that creates a pair of particles. Normally in empty space, they just rejoin a very short time later or a very short distance later. And then essentially you simply don't see it. But when you're near the surface of a black hole, near the event horizon, it's possible that one of those fluctuations, one of the pairs of particles, one of them falls in the black hole and it's not coming back. So now the other one, well, doesn't have a choice, but there are two possibilities. Either it falls in, and that's kind of boring, it just does what it does in normal space. But very occasionally, that other one has enough energy to go all the way away from the black hole and come out as some kind of radiation. And this happens over the course of the life of the black hole, but this lowers the energy of the black hole, takes mass away from it. And the black hole actually evaporates into a cloud of radiation through these quantum fluctuation processes. And that cloud radiation is called Hawking radiation. It was Stephen Hawking who first discovered it. But it simply comes from the same class of quantum fluctuations, same ideas of quantum fluctuations that Amber's talking about. But now it causes something as big as a black hole to actually evaporate into a cloud of radiation, photons, gravitons, electrons, positrons, everything, every kind of elementary particle there is. It takes a very, very long time, about 10 to the 70 years for typically a largish black hole, but it happens. These quantum fluctuations cause Einstein, the black hole of Einstein's, black hole in Einstein's general relativity theory, to evaporate into a cloud of stuff. And Amber's, in Amber's theory, Amber's cosmology, these same quantum fluctuations are happening on this tiny scale become entire galaxies when you magnify them through the expansion. So the thing about what's really cool about very strong gravity is it can magnify quantum fluctuations into a much larger, more macroscopically experienceable sphere.
So it's amazing to think, since both of you brought up quantum fluctuations in very different contexts, it's amazing to think that on the one hand, they're at the root of basically determining why the universe became the way it is. And at the same time, in the case of black holes, the opposite process of destruction, basically evaporating the black hole over an extended period of time. But we don't have a current theory that allows us to seamlessly talk on the same breath about quantum mechanics and the very successful general relativity. So what are the prospects for something like that to happen in the future?
Well, okay, I'll jump in. I mean, there's very good evidence that string theory fills that gap. It is a quantum theory, and it is a theory that contains gravity. And all the inconsistencies that are present in our previous attempts to making quantum theories of gravity don't seem to be there. Now, I'm hedging my bets because we've done huge numbers of calculations, and every time we tried to make a quantum theory of gravity before, we ran into all sorts of difficulties. We've run into none of those difficulties in string theory. It's just, I can't definitively say, oh, this is a quantum theory of gravity, because it's very hard to do the extreme calculations you really need to do to justify that statement. But everybody in my field believes, we've got a quantum theory of gravity, it's called string theory. And so now you've got to take that framework and do a new set of calculations. And so what I'm actually trying to do is to use that framework to describe black holes. And we can get onto the information problem in a few minutes, but there's a serious, serious problem when you try and follow up on the Hawking radiation story. And so, but I'll let Amber have a go at the.
Well, I mean, the thing that takes something from being just a theory to something that we believe is a fact or a law that describes how our universe works is experiments, it's observations, which is really why in our field, we're trying to observe the universe in the form of seeing the imprint of those theoretical gravitational waves that are generated when the universe was much, much, much less than 1 second old. Because the idea is, here is a theory that suggests that you should see this thing that should otherwise not be there. And if it is there, and if it is there in the way that the theory suggests it could be or should be, that is a smoking gun for the theory being correct. And so that's what we're trying to do with a framework. That's what happened with general relativity. It's what happened with quantum mechanics. Someone wrote down a theory, and then we looked into the extreme worlds with experimental techniques and said, oh yeah, general relativity predicts that we should see exactly this, and there it is, we see it. Quantum mechanics predicts we should say this, and there we should see it. String theory is a little bit more complicated because you really need these extreme phenomena in order to test it. And the predictions are, I'll let Nick talk about this, but the predictions are a little bit harder to get at. So we're really trying to figure out what is that smoking gun for something like string theory or a version of string theory.
Okay. So is the challenge here, so Nick, I want to get to the information paradox in a minute, but is the challenge here, do I understand correctly that we've essentially already seen the earliest light from the very early universe? So essentially we have a challenge because before that, it sounds like we were in this hot soup where even light is not getting through. So we're in a position where light is not going to be the next observable, right? It's instead going to be the subtle ways that these early fluctuations imprinted themselves into the light that we're observing right now. Is that the right way to think about it?
That's right, that light is still the observable, right? So the idea is gravitational waves are generated at time very close to zero. They travel through the universe. They are traveling through the Earth right now. And gravitational waves have been detected, and we can talk about this, but they've been detected not at the very, 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 very tiny level that we would need to detect them to see the gravitational waves coming from the early universe. They've been detected when we see things like giant black holes crash into each other and produce gravitational waves. So in principle, someday, way far in the future, we might be able to detect the gravitational waves coming from the Big Bang directly. We can't do that today, but we hope that we can see in the light. So the light is still the observable for cosmology right now, but we can see in the light the imprint of those gravitational waves that takes us then all the way back to time equals zero. But the detection of gravitational waves themselves is another really cool thing that has happened, and that over in the last several years, the direct detection of gravitational waves, and this came from an experiment called LIGO that I'll let Nick talk about a little bit because it is really about his field. But the idea here is, until just a few years ago, we had truly one tool for studying the universe. We had light. We had a whole spectrum of light, going all the way from radio waves to microwaves to visible light to X-rays and gamma rays. And we learned a ton from that. But all of a sudden, a few years ago, we also got like a completely new way of studying the universe in the form of direct detection of gravitational waves. And this is a hard thing to do. It's an amazing feat of technology and of scientific perseverance, but it's a new window. And over the next many decades, we expect this new window to produce all kinds of interesting things and to teach us about the universe in a whole new way.
So I definitely wanted to talk about gravitational waves and their detection, because this is a whole new type of astronomy, basically, that we're just entering the era of. Nick, could you give us a little bit of a perspective on what generates these waves in the first place, and what are the actual events that have been detected, what's actually been measured in the past few years, and how it fits to the predictions of general relativity?
Okay, so Amber showed these nice graphics a few minutes ago. If you can reprise the graphics, and then we'll move on to that other animation. But basically, if you put a planet, a star, or a black hole into space-time is not some rigid structure into which it's embedded. It's actually dynamical, and this grid, this lattice, this geometry evolves in response to the things that are sitting in it. So if you have two close planets or stars or black holes, they generate these ripples in the geometry, which then move outwards. If you can start it, and basically, it's as they in-spiral, they get quicker and quicker and quicker. But it generates a ripple in the fabric or the structure of the space-time, and LIGO detected these things have detected these merge. Oh, now you see it, and then when they merge, it goes quiet again. But LIGO has detected now something, I think it just hit the 50th confirmed detection. But this was the first this is a simulation from that came out of the first detection, which was 2015. I think it was announced about a year or so later. But basically, it's the same thing. You see these two black holes, and what you're seeing is a distortion of the star field behind them. And if you watch carefully, you'll see ripples going out across the star field. That's not the stars moving around. It's our vision, or what we see of the stars, and the light being deflected by the gravitational waves going out. And then once the merger actually completes, it goes completely quiet. And so if you cut to the next slide, you'll see basically this was the signal of the merger. This was Hanford in Washington, Livingston in Louisiana, two identical devices separated by a very large, half the continent, and they saw the same signal, which was spectacular confirmation of the merger. We've now seen about confirmed 50 such events. So it's an amazing achievement. There is also another instrument called Virgo, which does, and they're bringing more of these online. And in the not near future, 2037, I think they're going to launch a space, or they will bring online a space-based version of this, which this thing, the one we have, LIGO, has 4 kilometers long on a tube. This will be about 1 million kilometers long, and it'll be very sensitive to when the supermassive black holes in the cores of galaxies eat the stars and other black holes. And so we will see this kind of devouring that I showed you in the beginning, but actually happening through gravitational waves.
Were there any surprise? Sorry, go ahead, Amber.
I was just going to say, so as an experimentalist, I can't resist jumping in here and just saying something about how you measure this, because it is truly amazing. So LIGO is measuring what happens when those ripples in space-time pass through the Earth, and they literally squash and stretch and squash and stretch the Earth and space and everything around it. And what the way LIGO works is it measures the teeny little changes in a part of the Earth that is a vacuum tube, right, that has a laser going back and forth and is measuring the distance in 2 perpendicular arms. And LIGO can actually detect a change in the distance between 2 mirrors that is 1/10,000th the width of a proton. So another way of thinking about that is LIGO could measure, this technique would be capable of measuring the distance to the nearest star, which is 4.2 light years away, to an accuracy that is smaller than the width of a human hair. As a scientific feat of experimental genius, this is just brilliant. And the team did an absolutely remarkable job. And they worked on this for decades, and it really paid off. I mean, now we have a whole new way of observing the most extreme phenomenon in the universe.
For me, it's just stunning how experimentalists can deal with the kinds of things, because Hanford, you have to deal with trucks going by. That makes the Earth rumble. Then there's seismic noise. In Livingston, Louisiana, they actually built the thing up, and then about a mile away, they started cutting down the forest. And every time a tree hit, the thing would go off. How the experimentalists could see a signal in amongst all that sort of urban and seismic noise, it's a testament to their genius. It really is incredible what they did. But
Yeah.
We
It,
have,
it
as
really
Amber said, a
seems,
completely new window on the universe thanks to these efforts. And it's a proof of concept. We're going to just build more of these things and bigger and better ones, and we're going to see more and really cool stuff. And for me, one of the coolest things you can see is when you see something small glide into something big and in spiral like that. Because then, so I'm thinking about a small black hole merging with a humongous black hole in the middle of the galaxy. And then as it grazes the surface of the big black hole, you begin to probe the structure near the surface of the big black hole. For me, that kind of data is going to be really interesting, because that's where you start seeing what the guts of a black hole looks like. It really, and how it might possibly deviate from Einstein's theory.
I remember hearing about LIGO for the first time when I was a first-year graduate student. Just the idea that you're going to build an apparatus which is composed of everyday matter, like atoms, right? To measure the squishing and dilating that's happening on the scale of a tiny, tiny fraction of the atoms that make up the apparatus is something that I still can't get over, that this has actually succeeded. And it's just a testament to not just the ingenuity of the team, but also what humankind can actually achieve when they work in teams together, motivated by questions where they're curious what the answers are for. Nick, I wanted to ask you, since you've mentioned this idea of the black hole information paradox, to just take a couple of minutes, because that is at the core of your research, right?
Yeah.
Just take a couple of minutes, explain to us what the paradox is and why, again, this is a nice fertile area to look at this intersection of these two feats of 20th century physics, quantum mechanics, and general relativity, and what lessons we might learn from that.
So I just wanted to say, in sort of broader context, we're in a position which we're not used to being in before. Normally, as Amber says, we have a bunch of theories, we do experiments, we see which one's right. Currently, we have 0 to 1 theories, depending on whether you believe in string theory, that can actually deal with the quantum structure of the quantum properties of gravity. And so the information paradox is a sort of litmus test of whether you've got a viable theory of quantum gravity. So that means it highlights the problem, or one of the major problems of dealing with quantum and gravity. So one of the things that is built into quantum mechanics is that if you measure the final state of something sufficiently accurately, you can at least reconstruct the initial state of where it came from. So to use an analogy, suppose I've got some jigsaw puzzle that depicts a picture, but I'm not going to show you the picture. Then one way you can think about, say, burning a piece of paper or burning a piece of coal or burning a piece of wood, where you distribute the atoms across, the campus or something, is I take my jigsaw puzzle and I go out on the campus, I start throwing pieces in every direction. And then the next day you come along and you find a piece. And, okay, what's this? And then you spend your time pulling the pieces back together. You can then see the picture of whatever it was that was there. And so this idea, which is the sort of subplot of so many forensic science things on television, it's basically you measure enough details long after an event, you can reconstruct the event that actually happened. And it's fundamental to quantum mechanics. But here's the problem with black holes. In the analogy with black holes, you have this picture of the jigsaw puzzle being thrown out. So if I burn coal or I burn paper or I burn wood, I get atoms and smells and smoke and gases, which I can reconstruct what was burned. Well, gravity does something annoying. Basically, when you have a black hole evaporating, it happens the process starts outside the horizon, and nothing inside the horizon can communicate with that process. So all that happens outside the black hole is it depends on the mass and the charge and the rotation of the black hole, but nothing about how the black hole formed. And so this Hawking evaporation process basically creates a cloud of Hawking radiation that knows absolutely nothing about how the black hole was made. So it's kind of like taking the jigsaw puzzle that I had, and just gravity has the effect of putting bleach all over the pieces and washing them clean. And then you go around throwing them out around the campus. When you reassemble it, all you've got is a gray, bland landscape with nothing, just nothing. So gravity completely bleaches the information out of whatever went into a black hole. So in principle, if you make a black hole out of hydrogen gas or a star, or you make it out of old books, or you make it out of politicians, you should be, and then you look at the Hawking radiation, it's all the same. But quantum mechanics says, no, you must be able to tell by collecting enough evidence from the radiation to see what it came from. And so the quantum mechanics and gravity don't play nicely together. In fact, they are fundamentally incompatible. This process of being able to reconstruct the crime scene from the data that evolves out of it, you can't do it from Hawking radiation, which means that either gravity or quantum mechanics is wrong. Now, Hawking, when he first did it, came up with this. This is sometimes called the Hawking information paradox. He published the idea in about 1980 after his work on radiation. Thought he had to fix quantum mechanics. But the consensus has moved, we have to fix gravity. And it seems that string theory can actually solve this problem. And the way I sort of, in my analogy, I try and describe that is, imagine you got your bleached pieces, but you were given a microscope and you can scan the fibers of the cardboard and you can see, then you can sort of see little bits of coloration and you can reconstruct perhaps the color palette. And so by looking at the fine details using string theory, you can actually reconstruct perhaps the state of what made the black hole. That's the sort of information paradox in a nutshell. I hope I did it understandably.
It also sets up kind of the scale of the problem, right? We're talking about something where you're trying to unify some of the most incompatible theories that we've had in all of physics. Yeah.
The beautiful thing about the information paradox is it's one thing we absolutely know we have to fix. And it's really simply stated, and you can peel back the layer after layer after layer of that and try and figure out what's going on. That's what I do in my project. But the results of this are going to probably influence the kind of thing Amber does, because you really do need a quantum theory of gravity if you're going to understand the very earliest moments of the universe. So I have the advantage because I'm studying something which sits there for a very long time doing very little. And it's a good laboratory, but Amber and the theorists around their sort of cosmology are going to need this if they're going to understand the very earliest moments of the universe.
So I was about to ask Amber a question about some of the challenges, some of the biggest questions and challenges in cosmology research. And as I was looking through the questions that have started coming in from the audience, I realized that it's time to start asking some of those because they already intersect with some of the things I wanted to ask you. So let's start taking questions from the audience. Let's start with one that we haven't talked about yet. So there's a question from Valerie here, asking, what is the latest understanding of dark matter?
I think that's Amber's wheelhouse.
Yeah, so we haven't really talked about some of the things you can learn from looking at the microwave background. And the name of the game there for a long time has been to study that light, but not just to look at it as a pretty picture, but to really understand the statistics of those little fluctuations. And it's complicated to get from the statistics of those fluctuations to informations, right? So I'm just going to jump there and I'm going to say some of the things that you can learn by studying those statistics are things like how old is the universe? What is the geometry of the universe? And what is the composition of the universe? And we learn something interesting when you look at the composition. We learned that only about 4.5% of all of the energy density of the universe is actually the ordinary atoms that we know. Everything we know of is made out of. Trees and planets and people and water and everything. And the other, more than 95%, is made up of stuff that we don't know about. And there are two kinds of that stuff. So we can distinguish between two different kinds. One is dark matter, that makes up about 24% of our universe. And the other is some form of dark energy, which makes up just about 71.5%. And so the question was about dark matter. So dark matter is thought to be some kind of particle. It's probably a particle that just does not interact through the electromagnetic interactions that all of the atoms that we know about interact through. We can see the effect of it because it does interact gravitationally. So we can see the impact of dark matter, both in the microwave background, but also in some of the structure. And so there are experiments that are out there trying to detect what dark matter is. And it's hard because all of our experiments use the atoms that we know about, and those atoms interact through electromagnetic interactions. So if you're trying to find the dark matter particle that doesn't do that, it's a challenge. So that's the game, but it's probably a particle or particles that just don't happen to have that electromagnetic interaction.
Yeah, the other thing I'd say is that one of the places we're trying to make dark matter candidates at CERN, which is the largest particle accelerator on the planet, and there you slam protons together and hopefully produce some new stable weakly interacting particle that can be the dark matter candidate. The things that we know about, like neutrinos and things that are weakly interacting that don't interact strongly with light but have mass, don't cut it for dark matter. They can't describe it. It has to be something new. So this is one of the really cool things that happens between astronomy and particle physics. They go out and they find something, they find dark matter. And the particle physicists try and make models based on that stuff. And then we realize, oh, we don't have one of those. We can't, it doesn't work. And so we got to go find something else. And so one of the most promising places we might find is at CERN, but that they still have, we were hoping they'd find some dark matter candidate in the last 10 years, and they haven't yet. It needs to be stable, and it needs to be something that doesn't interact electromagnetically.
That is one to keep our eyes on. There's another question. There's actually lots of questions that I'm looking at from the audience here. This is a timely one. So this is a question from Tim asking, how excited are you about the new James Webb Space Telescope? And what are your expectations for how it will advance our understanding of the universe?
I think I'll defer to Amber first.
So the goals of the James Webb Space Telescope are really, they talk about shedding light on cosmic origins, but it really is not a telescope that looks all the way back to the beginning of time. It's really about understanding how stars are born, how planets are born, to look for exoplanets, right? To look for the potential for life on other planets. Super exciting stuff, I think, but not really the same kind of exciting stuff that we're talking about fundamental physics. There may be some clues there, but it's not clues in the same way of like looking back to what set off the Big Bang or how to unify quantum mechanics and general relativity. It's much more about, once you have a universe, how do the things that we know in this universe come about? Like, how do you get stars and how do you get life? So, I mean, I think, for example, the question of, can we learn more about exoplanets and learn more about the potential kinds of life that might appear on other planets elsewhere in our own galaxy and around the universe? I'm super excited about that, but it's really not my field.
And we're just waiting for the images to start coming in.
I was going to say one of the things about James Webb that's interesting, when you see it, you see these mirrors look golden, right? And the reason why is that they're optimized for infrared, and they're precise. So it's a superb infrared telescope, and you've got to get it above the atmosphere so it can really be optimal in the infrared. And that's exactly what you need to see cocoon nebulae and see inside the star formation regions and so forth. So it's a perfect instrument for doing that. But it's looking not at the visible spectrum so much as the infrared.
So we'll do one or two more audience questions. Here's a fun one to think about. So from William, if the universe and time is infinite, why do we believe there was only one Big Bang? Well, let's start there. Do we actually believe there is only one Big Bang?
First of all, I wouldn't say the universe is necessarily infinite, and I wouldn't say time is necessarily infinite. So, we think that the universe as we know it is about 14 billion years old, so that there was a beginning of time in our universe, at least the way we calculate time. Now, could our universe have gone through cycles of some kind that make there be something before our time t equals 0 or beginning of time as we know it? Sure. And do we think there's only one universe? We don't really know, right? I mean, that's why we really need to understand, how did this universe that we live in evolve? Where did it come from? Because if we can understand the fundamental physics in which it is embedded, that gives us a real clue about whether there might be others. So I wouldn't say no to that.
But the existence of other universes is kind of a hypothetical, in the sense of, well, how do I interact with it now? How can I measure its presence? Now, Amber's absolutely right. You can still talk about other universes, because if your theory that governs our universe can contain an evolution that will involve multiple universes, it might give you a clue to answer that. But today, I don't know, I can't really say there's another universe because I have no experience. There's no way I can interact with it. I can't just post a letter to the other universe or send. So it's very hard to address that issue observationally, experimentally, because we just live in the universe. But the only way we can honestly answer it is to figure out how our universe came into being and then run in with that and see what else we can do.
All right, so here's another question from the audience. What evidence is there that the baby universe was microscopically small? Could it not have been large or even infinitely large at the moment it first began to expand, as long as it was also very hot and dense?
So a lot of work has gone into this. And I think probably the best evidence is the nature of those fluctuations, right? So if you look at the characteristic of the fluctuations in the microwave background, they have the characteristic of quantum fluctuations, which is really suggestive that that is where they came from. There's also evidence that has to do with the geometry of the universe and has to do with the dynamics of the universe. That's a little bit harder to talk about, but also points in the same direction.
I'd also add that really the best thing you can say that's most accurate is our part of the observable universe came from something absolutely microscopic. But the entire universe could in fact be infinite. And so therefore what it came from were an infinite number of microscopic things. So how you choose to describe it. But the important thing is that what we observe in a sphere that's 14 billion light years in radius is that much of it came from a microscopic fluctuation in a very early part of the universe. But the whole universe itself, it's hard to say whether it's finite or infinite, but it was infinite. Well, it was incredibly highly compressed, so that a galaxy or cluster of galaxies came from a quantum fluctuation scale of thing.
So here's one that I remember stumping me when I first learned about it. So this is a question from Wayne. If light is coming from 14 billion light years away and the universe is constantly expanding, shouldn't it take a lot longer than 14 billion years for light to get here because of that expansion?
That's a good question.
Okay.
You want to take that one or you want me to try it?
We can go either way. Basically, what is actually happening is that the universe is expanding, and as the light flies along, the universe is actually getting large. The scale of the universe, the spatial universe, is actually stretching. So it's kind of like an ant walking on an expanding rubber sheet. Yeah, it's gonna have to catch up, but what we do when we calculate the expansion of the universe, and we talk about the light getting to us from some other place in the universe, is we allow for that expansion of the universe in the dynamics of the expansion process and asking, well, where did this photon come from? And we run it back using the expansion of the universe and the expansion of space, and we figure out where it came from. I don't know, you can probably do better than this.
So the way I would think of it is, how does light interact with that expanding space-time? So light is actually embedded in that space-time in such a way that it's, I think of it less like an ant crawling along the surface and more like the light particle itself is being stretched along with the space-time that is being stretched. And you see direct evidence of that. So I mentioned that we are observing the cosmic microwave background. That means the light we are observing is of a wavelength that's sort of about this big. But we know that the light that was emitted was of a wavelength that's much, much, much tinier, right? It was really ultraviolet at the time of emission. And the idea was that very small wavelength was stretched as the universe expanded, so that now when it hits our detectors, we need to build microwave detectors to observe it. So it's not that it's slowed down as so much as it's stretched out by the time it gets to us.
So the light itself has been stretched by the expansion of space-time, right?
Correct.
Indeed. So there's two things that are going on. The light is flying across space, and space is getting bigger. But as the space stretches, it stretches the photons, and exactly. And so basically, the wavelength of the photons gets longer and longer and longer in direct proportion to the stretching of space as it travels through.
So I wanted to say that we are at the 1 hour mark. However, we do have more questions coming in from the audience. So if you two are available and you wouldn't mind spending another couple of minutes before we wrap up, we have the go ahead from our producer to go ahead and do that. So Nick, maybe this is one for you. So because we've mentioned string theory, there's a question here from Sundar asking, can you explain in very basic terms what string theory is and how different it is from loop quantum gravity?
Oh gosh, loop quantum, okay. I'm not the right person. I'll explain what string theory is. Loop quantum gravity is another idea about quantum gravity, but it's, okay, I'm not going to go there. String theory, the basic paradigm, we normally start off when we do quantum mechanics and so forth, we think about particles moving in a space-time. And then we think about, in quantum mechanics, we think about probability distributions of those particles going in certain places. The starting point in string theory is you start with an extended object, a string, quite literally, something which is an elastic tube that can be either closed or open. And then what happens is normally, the elasticity is so powerful that normally it just behaves like a particle. The elastic band is snapped shut. So in almost every respect, it starts out looking like a particle. But if you put a lot of energy into a very small part of the space-time where there's one of these particles, then what happens is it starts to stretch and vibrate and fuzz out. And so the nature of space-time, basically changes when you pump too much energy into a small volume. And this is to some extent how it softens the quantum properties of gravity. So it's a different paradigm from right from the starting point. And then you have to sort of reinvent almost all of modern physics based on that paradigm, that the starting point is not particles moving in space-time. It's extended objects that collapse to points under low energy, but then the wave function or the so forth becomes a function of this extended object. And if you put too much energy in, it starts to fuzz out and space-time becomes fluctuating.
Thank you for that. Maybe this will be our last question for the day, and it's one that intersects with popular culture, so I thought it would be a nice one to maybe end with. There's a question here that's related to the movie Interstellar. And the question is there any scientific support for the ability to jump through time and space via black hole? I guess this is a question about what happens at singularities, right?
Okay. The answer, and don't rain on the parade. It's when you build models in general relativity theory of black holes. There are extensions of black hole solutions that look like you can make wormholes that can jump through space-time to some other point in space-time. Generally speaking, those wormholes are pathologically unstable. So what happens is you can build this beautiful mathematical model that fits with general relativity theory that suggests that a rotating black hole has some cosmic plumbing that will take you to another universe or another part of the universe. But you drop one particle in that cosmic plumbing and the whole thing goes and collapses. So cosmic plumbing is generally pathologically unstable. The minute you drop something into it, it's gone. So really, we don't think it exists because it's so unstable that really, while it exists as a mathematical solution to the equation that's kind of cool to think about, it's very hard to make it actually work. Now, that's an answer in general relativity theory. In quantum mechanics, when you add a little the quantum to it, there might be short periods of time in which such things could exist. And so quantum wormholes, maybe.
That's a very theorist answer. Let me give a more experimentalist answer. If in principle that could happen, the inconvenient fact is that in order for any macroscopic object to travel through a wormhole, they would have to be compressed to very near infinite density. So even if there wasn't such an instability that Nick describes, you would be squished to certainly not surviving the journey. So in terms of raining on the parade.
Yeah, exactly.
I guess that settles that mode of travel.
So people are hopeful that maybe something of the quantum world, but indeed only quantum objects can take advantage of it. You and I, no, sorry, we will be squished.
All right, so I guess we are coming up on time here. So I wanted to end just as I started by thanking Professor Nick Warner and Dean Amber Miller for participating today. Thank you for taking the time, and thank you for entertaining the audience questions as well. And I also wanted to again thank our audience and remind them that if you enjoyed today's discussion and would like to find out more, read the latest issue of USC Dornsife magazine, which is all about the cosmos. In that issue, you can read about Dean Amber Miller's first major experiment as an astrophysicist in the Chilean high desert, eavesdrop on a conversation between two Dornsife cosmologists to learn more about dark matter. So one of our audience members asked about that already, dark energy and black holes, and what happens when you fall into one, which is a conversation we basically already started. And you can even, in that issue, explore how to best communicate with aliens. It's all in a day's work here at USC Dornsife. Thank you, and see you next time in the Dornsife Dialogues. Thanks.
Thanks indeed.